physics, we know a lot about the universe. We can construct theories that describe what we see and predict what we have not seen yet. For instance, we can observe a ball falling to the ground many times and formulate a physical theory for its motion. This theory will tell us how other balls will fall to the ground. One such theory is special. It's called quantum field theory. It's special because it can describe the behavior of the tiniest particles that we know, like the electrons inside atoms. The same theory can tell us about magnetic materials and superconductors, even though their size might not be tiny at all. So quantum field theory is very versatile and can take many different forms, with different purposes. Theories describing very weakly interacting particles are called weakly coupled and are very well understood. Physicists have developed a systematic procedure to make calculations with them that work like a charm. For instance, a quantum field theory governs the behavior of electrons and photons, the particle associated with current and the particle associated with light. In this context, we can make predictions that are verified up to 12 decimal numbers. This is like computing the age of the universe with a precision of a few days, or launching a golf ball across France and predicting where it will land with a precision of the size of a bacterium. Other quantum field theories describe particles that interact strongly. They are called strongly coupled and are much less understood. We do not know how to use them. For instance, we know that a quantum field theory describes the particles inside the nucleus, but we cannot calculate its predictions. It's very frustrating. Perhaps something can be done, however, by asking a question that seems even more complicated. How many different quantum field theories are there? If we get to know all that quantum field theories can and cannot do, we necessarily learn something. So, we need a map of what all the quantum field theories are and can do. But how can we draw this map? Well, we can imagine an experiment, similar to the one performed in particle accelerators like CERN in Geneva. We are not actually building the experiment, but just imagining it. We imagine particles colliding and look at all possible imaginary outcomes of this collision. We imagine crazy things. The result of the collision must, however, be consistent with quantum mechanics and special relativity, Einstein's theory. These tell us, for instance, that the outcome can only appear after the collision took place. This looks obvious from our point of view, but happens to be a strong limitation in the fantastic world of quantum field theories. We also know that the probability for a particular outcome, for instance for getting back 2 particles instead of 4, cannot be more than 100%. Again, something obvious from our macroscopic perspective, but very limiting in the world of microscopic particles. So, from what we have imagined, from our wildest dreams, not much remains. And what remains is a candidate for a healthy quantum field theory that can be associated with a real material or perhaps describe a real particle. This approach, called bootstrap or S-matrix bootstrap, could perhaps help us find new materials. One of the hopes is that it will tell us something about room temperature superconductors, which are materials with enormous range of applications, from improving medical imaging to fundamental research to super-fast trains. Knowing about quantum field theories can also teach us why our universe is the way it is, and perhaps help us find the theory of everything, a quantum theory of gravity, the holy grail of theoretical physics. Perhaps one day we will be able to calculate the incalculable.